So what I'll talk about today is the software I've been working on since my PhD, really, to make grids of stars. So this would be using the binary C code that we described yesterday to run thousands, millions, maybe even tens of millions. I think the most we've ever run is about 171 million or something in one grid on a cluster, which is quite a lot of stars. I mean, it's not a whole galaxy, but it's a big cluster. So now that's called the binary grid software. It was originally written in Perl, and the reason for that is Python didn't exist when I started writing it, and going back and rewriting big chunks of code and debugging it is a very expensive thing to do. There's a lot of features in the binary grid which make it very easy to use on many different systems, like on condor systems, slurm systems, multi-core systems, this kind of stuff. So there's a lot of debugging's got into that. And one of the reasons a couple of years ago that I completely rewrote binary C so that it was thread safe and it had a shared library and an API interface was to get the grid to work faster. Because up to that point, it was about half as fast as it is now. A factor of 2, that's a lot. So you want to do that. It's also one of the reasons that binary grid has a lot of optimization in it. For example, there are often chunks of the code you'll say, well, why have you done it like this? Well, the reason is to make it as fast as possible, usually. I try to make it so it's not unreadable, because of course code needs to be maintained, but you do need it to be fast. If you're going to run 1 million stars and you can shave off 1%, that's quite a lot. Okay. CPUs cost. Even in a university, CPUs cost money. That comes from my grant, or it comes from your grant. Or if you're lucky, you get free time on Dirac, but if you want a suitably large amount of time, then you're going to have to pay. Even if it comes out of your overheads at the university, you still get paid in some way. So. Okay, so why Perl? Well, because Python didn't exist. But Perl, I mean, if you don't know it, Perl is actually very fast and very good at what it does. Fully fledged programming language. There's very little Python does that Perl does. So it's actually nothing, I would say. I can't think of it. And binary grid 2, which is the second version of binary grid, is fully object-oriented. So you get all of that as well. So you don't have to worry about ancient programming techniques. It's all object-oriented. It's fully multi-threaded, so you can run it on however many CPUs you have. You have 4 on your laptop, like I do on 4 cores, like on here, that's fine. It'll run automatically on that. If you have 16, it'll run on that. Of course, like any multi-threaded code, as you increase the number of cores, twice the number of cores, you don't actually double the number of systems per second. And the reason for that is that usually it's memory limited rather than CPU limited. So your CPUs will be going at max, but that's not what the limit is. It's all the moving memory around inside the code that's really the delay. And that depends on the bandwidth of your CPUs. Different CPUs will give you different results. Really different. So in fact, if you buy a whole grid of new Xeons, which are very expensive, you don't get the same performance as you did, well, this was a few years ago, but you don't get the same performance you get for the same price for just normal i7s. They actually, because they have slightly more memory bandwidth, which was kind of weird, but that's why I ended up getting 16 of them instead of 16 Xeons. And it was half the price. Could somebody get the door? Thank you. So there are multiple modules which support the binary grid. There's one for the initial distribution functions. These are like the initial mass functions and stuff like that. There's also one for doing different grid spacing functions. So you automatically change the grid spacing however you like. We're going to look at an example, the template script, which is in at this location, source Perl scripts 2. The 2 on the scripts is because it's binary grid 2 rather than binary 1. And it's called the template. So let's go through this. Now, one thing I'd recommend is that to install Perl, you do what you do also with Python, which is install your own version. Don't rely on your system Perl, because system Perl often, particularly noticed here, if you're using one of the computing machines here, you don't have write access to install new modules or things like that. That has to be done by IT support very often. I know that's true in Cambridge as well sometimes. So it's a nightmare. It's much easier to install your own. And you'll find that in the documentation, there is a whole section which tells you how to do that. It's very easy. It takes a few minutes to compile it, but once it's done, it's done. So you don't have to do it twice. And then you can use this thing called cpan- or cpan-m, as it's known in the command, to install modules. So if you have a module in a zip file, a gzip file, you can just immediately call it, install it. There's a script inside binary C called install modules, which we'll go through all of the ones that are there. So you don't have to worry about that too much. Now, do this while you've got power plugged in on your laptop. It'll take a little while, but once it's done, it's done. And it's very easy. Okay. So in the template, you will see what we do is we try to set up a population of stars. Do you have a question, Jim?
No, I'm actually prepared for my next talk. So
Okay.
the question was about that.
Okay, that's fine. So make sure. If anybody else has a question, just interrupt, please. It's beautiful. So to make a new stellar population, you do the usual object-oriented thing, and you call binary grid 2, which is the module, and then you say you want a new object. And in this case, I'm calling the object population. So in Perl, you put a $ in front of variables. It looks old-fashioned, but it works. And you can give it options for that population. So I've given it here that the metallicity is 0.02, and it evolves up to 15,000 megayears. It's roughly the age of the universe. You can also set the number of threads. So that's the number of CPU threads that you want to run on. That's also possible. Okay. So actually, you have two sets of options here. One set of options is, and they're handled internally, so you don't have to worry. But one set of options is for the grid. The other one is for the actual binary star code, which in that case is binary C. So for example, metallicity will be passed to binary C because it recognizes it as a binary C option. N threads is clearly not a binary C option because binary C only runs on one thread. And so N threads is a grid option. So, and this is how it will continue to work. Now, given that you've made a population, you can set later any of the variables just like you do when you construct it. So here, for example, I'm turning on the verbosity, which is how much logging you have. If it's 0, it's pretty quiet. If it's 1, you get every some 30 seconds or something, I think it is, you get an bit of output to tell you it's alive, how it's doing, things like that. And if it's 2, you get loads and loads and loads, but that's when it really breaks. So I can set all of the different things with a call to the set function. And then to evolve the population, once you've set it up, is easy. You just call the evolve function. And then it just sits there, it evolves the population and returns whatever it is that you need. So it's really like an object-oriented code. There's no issues with this. But what you have to do is to link binary C to your code. Now, we saw a bit of this, what David was doing yesterday with the Python, and the Python stuff is all based on what we do here. The way we normally do this is to use the printf statement. So that's this one here. It's with the capital P. Remember, we use that so everything gets put in the buffer, not straight to standard out. And the old-fashioned way of doing it, which I still use quite often because it's very easy to do actually, is to put a printf statement in your log every time set function. And then that gets swallowed by your population object, and then you can pass it in your template script in this case, or whatever script you call it. But in order to do that, you have to rebuild binary C. You have to rebuild the library, and you also have to rebuild the binary grid module. Because what you've done is you've shifted all the stuff around inside the shared library, the libBinaryC.so, and if you try to run that directly with an old build, it will segfault because it's looking at different bits of memory that don't exist anymore or in the wrong place. You don't want the segfaults. That's unfortunately the way that Unix systems work. It's the way Windows works. It's the way everything works. So you know that's beyond our control. However, there is also the auto logging, which you kind of saw yesterday. There are two ways to do that. The first way is to give it a list of variables like this. So I've given it here the time, the mass, the probability, and the time step. And then those will be output every time step. Okay. They're output with a header string, which is my stellar data in this case. Now, the reason that you do that is so that you can have different types of output for the same build of binary C. So binary C can output some stuff that we want to pass, but it might output other stuff that we don't want. And what you can do in your script is to then look at what the header is, and you can decide whether to include that data in yours or not. So you have control. The downside of this is that it assumes that all of these variables are floating points. Okay, because it doesn't know whether they're ints or doubles or whatever. Now, if you cast an int to a floating point, you get a number that's quite reasonable. So I think that's okay. It's not really a problem. And it uses the %g, which is the standard sort of generic floating point output in the C library. That will give you an integer if it's an integer, and it will give you a floating point number if it's got a fractional part. So I think that's fine. And for most things, this will work. But you may want to have a little more control, at which point you can actually set the code manually yourself. So here I've got the code which is identical to what that previous one was. This is what it would generate. But of course, you can also put if statements in here. So you can say if the star is this, if the time is this, if the chemistry is this, whatever. And you'll see lots of examples in the log every time step function about how to do that. There's a whole system. Now, the good thing about this is more flexible, so you can actually put %d, which is for an integer, instead of %g, or you can put strings in there, or you can put anything. You can really put a whole chunk of code in here. I mean, you could, in theory, completely obliterate star data and do whatever you like. It's like a hook, like in Mesa, where you have these hooks. It's kind of like that. Okay. But please only use it for logging, otherwise it's not really supported. So it's this myStella data that is the useful part. Okay, that's the link between your C code and your script. Now, of course, you could put anything you like in that header. It could be any string. Armand's Novi or something. That could be fine. So, but make it something that's obvious to people working through it. Now, how do things actually work? I'll give you a little bit about how they work in the background. So binary grid 2 has to talk to binary C. It does that through the shared library in the API. Okay, so the API, that's what APIs are for. That's the whole point. The output is put in the buffer. It's the binary C buffer, which is allocated, and is then loaded into the Perl script as a series of lines of data. And what happens is you loop over those lines of data. You keep going down the stack until you get to a line that says fin, meaning finished, and then it stops. And that's set up in the, you have to set that up yourself in the grid script. Libbinary C is completely thread safe, so you can run it repeatedly as you like, which is good. I should say that's why we don't have global variables. I know I said this yesterday, but this is why. As soon as you have global variables, this will not work. Okay, so please don't. Or at least global variables that are writable. If you have read-only global variables, that's fine, but if they're writable, it's a problem. So how does this look in the script? So I said we have a loop. The loop is here. That's your while loop, classical coding while loop. And know that it's a while one, which means it goes on forever. We'll see in a minute that it's not quite true that it goes on forever. So what you do is, the first thing you do is you call the TBSE line function. That gets a line from the binary star evolution code. So this is where you're looping over the buffer line by line, and it automatically splits it into lines for you, so you don't have to do anything. And what this line actually is, in this case, because I've set it up to do this, is the line is actually not a line, it's an array of objects that were in that line. So if the line is it has the header and then it has some data objects after it, it splits it on those spaces to give you an array. So you don't have to do that, that's done automatically. Which is probably what you do anyway. So the first thing it does then, well, other than printing out what's in that line, it gets the header, so it shifts the first item off that array, puts it in the header string, and then this header is the thing we called myStella data before. But of course, the exception to that is when the header is fin, meaning finished, then you should stop. So you break out of the loop if the header is the fin. So next, you check whether the header matches what you expect to find. In our case, myStella data, and if it does, you can do something with the data. Okay, what you do with the data is up to you. That's not something I'm going to prescribe, but I'll give you an example of what we do here. But that's really the part that I don't want to program for you. In order to set this up, you need to write a function to do it. So here I've called that parse data, which just means you go through the data line by line. That will take two arguments. The first one is the population object. The second one is something called results. Now, results is what we call a hash in Perl. It's like a dictionary in Python. Why it's called a dictionary, I don't know, but it's fine. It's as if, let's ignore 30, 40 years of computing. But the hash, as far as I can tell, they're identical. So in this regard. So the hash will take, it's like an array, but it takes strings or objects or whatever instead of numbers as an index. Okay, so, and the reason for that is that you can then make very, very powerful nested structures. You can put hashes inside the hash. You can put arrays in there. You can do whatever you want. So if you've got a histogram, you can put it in there as an array. You can also put it in as a hash if you prefer. That's absolutely fine. And I'll show you an example of how to do this. But this results, this is what you want to fill. So this is the thing at the end, which is added up. And let's say you've got, I don't know, say 10 threads running. What you don't want to have to do is to manually join all of the data from those threads. That is all embedded in there automatically. Okay, so there's a module which it's one of the additional modules that I programmed in. It's based on something I found on the web, but it adds up the hashes in the way you'd expect. Okay, so numerically it adds it correctly. And of course, they all have the same format because they're all set in the same function. So it's pretty straightforward. So that's all done for you. So you don't have to do anything other than just set the numbers. Why have I gone backwards? I want to go backwards. There we go. Okay. Maybe I do. No, that's fine. So when you eventually want to do the data analysis, I put that in a separate function that you call after you've done the evolve. That's fine. And then you can just access this population results object. You get it from the population by calling the results function. That's very easy. You can set it in here. And then you can show what's in it. You just loop over whatever you put in it. So that's relatively straightforward, and that's the last thing you should do in your script. You could then also do stuff like data processing, make plots if you want, you can do whatever you like. I would highly recommend doing the plotting separately from running populations, because you want to keep everything in small chunks so that if something goes wrong, you can go back and you can do it again. You don't want everything in a big long chain that you have to do in one shot, because if things do go wrong, they do. Sometimes it's not your fault, sometimes the power goes off or something, and this happens. You want to be able to rerun, not the whole thing. So at this point, I would actually recommend in output, send output to a file in whatever form, and that works pretty well. Now, to set up the grid, it's a little more complicated because you need to decide how many stars you're going to run on the grid. You've got to decide the range of masses of your stars, which is relatively straightforward. And to do that, you use the add grid variable function in the population. Now, what this does is to automatically set up the grid for you, so you don't have to write any of the loops. It's all done automatically. The code's generated for you. But you do have to tell it a few things. So in this case, I'm looping over the mass, or rather, I'm looping over the log of the mass. The reason for this is that often you want to run a log mass grid because more stars are in the low mass end, and things vary more quickly at that end, so that's where you want to put them. But in this case, I'm running 1,000 stars, so it's quite good resolution compared to what we normally do. You can give the grid variables names. So this one's just called the primary mass. I've set nmin and nmax to 0.1 and 80. So that's whatever you like. And I told it the range. You just put that in an array in here. The resolution is the number of stars, so it's fine. It's just, that's an estimate for it. So, spacing function. Now what this is on the grid, you have to decide what the gap is between the stars on the grid. And in this case, that's just a constant in log mass. Okay, so the minimum is log of min here. The maximum is log of max, and then just the number in the grid. That's all you have to do. Now there are various functions in the spacing functions module you could use. You don't have to have constants. It's just the simplest. The pre-code is code that's executed at the beginning of this chunk of the loop. And what we do there is we construct the mass from the log mass, because the mass is what you actually need to call binary C. So you have to do that. We then define a probability for each system. And in this case, that's the Kruper IMF, which we saw yesterday, I think. It's pretty standard. The reason we multiply by n1 is because it's log mass, not mass. Okay, so you have to convert. You've got the 1 over x integral. Then we say we're using the method called grid. There are two methods that you can use in the latest version. You can either have a gridded code, or you can Monte Carlo it. So you can run them randomly. The grid is almost always better. You guarantee resolution if you run a grid. Monte Carlo doesn't guarantee resolution for the same number of particles or points or stars, whatever you want to call them. Also, Monte Carlos have this unfortunate blurring of data, so you don't really have any idea what your resolution is from your results. Whereas if you have a grid and you see stripes in your output, you know your resolution is not sufficient. So if you use Monte Carlo, there's always a sort of blurring. But it's up to you which one you choose. The grid can be edged or centered, depending on which you want. Normally you want the point to be in the center, but you can also put the point on the edge, depending on where you want your grid to represent. It's just an offset. This is standard, and this will be good enough for almost everything you do. So we have a template script. We're going to go through that. It allows you to set up single or binary stars. Of course, in that grid, I only set up single stars, but we'll go through the binary stars in a minute. What the template does, it calculates an initial mass function and then an average mass function, assuming a constant star formation rate for the population. So let's go through the template and see what's in there. And the reason I do this is because I know a lot of you aren't familiar with Perl scripts. Just to show you, they're not very hard. All you have to do is copy paste it. You can alter things yourself. It's very easy. So the first bit has this stuff at the top. I would just recommend copy pasting that. This just says, the first line says use Perl. Use strict is like, was it implicit none in Fortran? Those of you know that. That means you can't define dodgy variables. Use 5.16.0 just means use all the features in version 5.16. And that's absolutely fine. And then the obvious things, use binary grid. You know that, because you've got to use binary grid. Use binary grid C. We have two backends in binary grid, the C1 and the Perl one. There's the Perl one we kind of discussed yesterday with the pipes and chalking. That's not supported anymore. It should still work, but it probably won't. So please use the C1 because it's twice as fast and it does everything better. At some point, I will completely deprecate the Perl one, but I know some people somewhere are probably using it. And then this other function here just counts, this is the end CPUs function. We use that down here to count the number of CPUs. That's so we can set the number of threads. If you don't do that, it will automatically do it for you, but I wanted to make it explicit that you could change the number of threads. Everything after a hash symbol is a comment, so obviously don't worry about that too much. So what we do then is we set up the population. That's the first thing here. So the call to new, you've seen this before. Copy pasted this, nothing new. So we set up the population object, and then we can switch on loads of stuff in there. So I'm switching on, I want to save the arguments for each file. The reason I say that, log args is very useful if you're ever debugging and you want to know which stars are running at a certain time. If you set log args to 1, it saves files in /temp to tell you on which thread your argument list is. So that's the argument string like we had yesterday. Other things that are maybe useful, return array refs, that's quite handy. That's what I said before. You can either get lines from the output or you can have it automatically split into arrays for you. This probably makes it quicker. I've turned verbosity to 1 because that's what I recommend you use. That always gives you every 30 seconds or every 5 minutes. You can set the time. This one, log dt seconds. You can set that to whatever you like. I think it defaults to 30 seconds, so it tells you it's alive. And then I've set the logging to tell me I want to output the time, the mass, the probability, and the time set of each time set. There's also this call here to parse args. What that does is it goes through the command line arguments you've sent to the script. Now that's very useful if, for example, you're running several different grids and you want to put them in a loop in a bash script or something like that, or a Python script or whatever. And then you can just call this from that Python script. It's slightly different, say metallicity or something like that. And then whatever's on the command line, let's say on the command line you put metallicity equals 0.01, that will override the metallicity at the top there. So it does that in as smart a way as possible. So you have another layer of control, which is useful. Now we set up the grid of stars. Okay, now we've already seen the single star setup. That's this one here. So I'm not going to go through that in too much detail. But if you set duplicity to 1, that will then instead make binary stars. So I put an example here for binary stars. First of all, we set the resolution, and they're all, this would be a 20 by 20 by 20 grid. You can change that, of course. If you want to take too long. Again, the minimum maximum masses. I've set the binary option to 1 because I want the population to run binaries. And the first grid variable looks pretty much identical to what we had before. That's just the primary mass in the binary. But then what we do is we add another grid variable. So in this case, we add the secondary mass, or rather the mass ratio in this case. Now it's a little more complicated because you require, this thing here is called a condition, so that this will only be executed if this condition is true. But that's okay because we set that above. The binary is 1, so that's fine. The reason that you put that there is because you can also have mixed grids, which have both single and binary. So you only want this to apply to the binary part. The mass ratio is called Q. That's standard in binary physics. Long name is mass ratio. The range is between 0.1 to 1, but it's actually 0.1 divided by n1. Okay, and the reason for that is that the minimum mass of a star is 0.1. So that's why you can't have a mass ratio of 0, because that implies mass 0, which is clearly wrong. The resolution we set above, so that's easy to see. That was on the previous slide. Again, the spacing function, I'm putting it constant between the minimum and the maximum with whatever resolution. It's very simple. And again, we need some pre-code, because binary C takes M2, it doesn't take a mass ratio. So you have to calculate what M2 is, but that's easy, it's just Q times the primary mass. Now the probability, I've put here a slightly more complicated one. This uses what's called the flat sections code. This is where you can have multiple sections that are at different heights in your probability density function, for example. Here, actually, I've set all the heights to 1, so there is just flat between the minimum and maximum. So it's very easy. But you can change these as well. So you could, for example, compared to the distribution we saw from Abhinay yesterday, you could set up multiple sections in your mass ratio. You could have as many as you want, and it will automatically then just calculate the probability for each of those. And again, it's a grid, centered grid that we're running this on. Should be easier now to go through to the next one, which is the period distribution. I'm using the Duquesnoy-Mayor period distribution, which is valid for low mass stars, probably not high mass, but it's all right for an example. Everything here is pretty similar, except for this section here, which is the pre-code. Again, you calculate the period from the log period. I'm also calculating the separation here, because you can use Kepler's law to do that. There's a function which will do that for you. And so if you will need to do that, just copy paste this. I also set the eccentricity to 0. And the reason for that is we're not looping over the eccentricity. You could just add another call to set up another variable in the grid. Normally it doesn't matter. Now the Duquesnoy-Mayor distribution has a Gaussian distribution in log period. And these are the Gaussian parameters, I guess the mean and the dispersion. And these are the range of the Gaussian between the min and the max. So that's all it does. And the reason that you need to do that is because you want to normalize the distribution to have an integral of 1. It's a probability density function, so it should integrate to 1. And if you don't give it the ranges, of course, the Gaussian goes on forever. And so it would be a very long calculation. If you don't work there. So do we have any questions on this before I go on? I mean, I want to make sure, because otherwise it's going to be... Okay. So the rest of the script is then you just link the function pointer inside the code. A function pointer in C just points to a function. So that you tell it, what is the function? Well, the parse data function is the one that goes through and passes the data. That's very easy. You can ignore these things, but I mean, if you want to show the version string, so that's the binary C version string, you can do that at this point, which is actually quite useful, because if you're running a grid, the version string will tell you what the version of the code is, what the Git revision is, the date it was built, what compiler it was built on. So if you want to debug and you want to go back and look, it's very useful to output that. You can also show the argument list that's available from the code at any time. So you can use this function to do that. And that's something that's quite handy. So that's just for debugging, really. We then evolve the population, and then we call the output function that we saw before. And then we're done. So we exit. That's all there is. So parse data, you've seen bits of this already. It takes the population and the results hash in. Now, one thing we do slightly differently in here, I didn't mention before, is you can also grab the progenitor information. And this is not directly from binary C, this is from the grid itself. So that's M1, M2, the period, the separation, and so on. And so I can calculate the progenitor initial mass. Now, if the duplicity here is 0, this part just gives us 0. That's because that's the secondary mass. The secondary mass is clearly 0, and you've got no binaries. But then if you have binaries, so duplicity is 1, then this part here is what you get. So then the initial mass is M1 plus M2. That makes sense. The probability you can also get from the progenitor. It's very easy. And then what I do is I use the rebin function to bin the initial mass to within 1 solar mass. Now, this is something that often catches students out the first time they run the grid. What you don't want to do when you're making an initial mass function is to save every initial mass, because there's a huge number of them, 1,000 of them in this case. What you want to do is bin it and make a histogram. And so what the rebin function is to actually do the rebinning for you to whatever nearest one solar mass. In this case, you could set 0.1, you can do what you want. But if you set that to be, well, if you don't do that, what you'll end up with, particularly when you run binaries, is you'll have 1,000,000 points if you've got 100 by 100 by 100 grid, or in this case, what's 20 cube? 40,000. 20 cube, it's more than that, 80,000. So it's 20,000. So it's, it will give you a huge number of points, and that's not what you want. And then you'll fill your RAM, and you'll ask me, why does it crash? And I'll say, well, that's because you're outputting too much. A lot of people do that. Don't fall for it. Rebin is very useful. It's built in. It's very fast. So, and then what I do, now we have the binned initial mass, I can set the initial mass function. So remember, you set all your results in the results hash. That's this one here. And then the initial mass function here is the label of the hash. So that's, remember, hashes are labeled with strings rather than numbers. I've called it the initial mass function. So initial mass function is actually a hash itself, which then I am putting in this binned initial mass as the label. And then I'm just adding the probability in the bin. And then later we'll see that we can go through this and reconstruct the histogram. Then we have the while loop. You've seen this before. There's nothing new here except for this last bit here, where again, I'm binning the mass as a function of time. So remember I said this is the average mass function for a real population. Not the same as the initial mass function, of course. But here I do exactly the same, bin it to the nearest one solar mass, and I just add it into the mass distribution. It's not the initial mass distribution, just the mass distribution. And in this case, what we're doing is we're not adding the probability in there. We're adding the probability multiplied by the time step. Because the number of stars will depend on how long the stars spend in a given phase of evolution. So that's why you have to add the probability times time step. Now, this is a fundamental concept. If you're counting something that's instantaneous, say supernova rate, you'd use probabilities. The birth of a star is also instantaneous. It's time zero. That's also probabilities. If you're counting the number of stars that go through a certain phase, you have to use time step weighted probability. Which makes sense if you think about it, but you've got to get that right, otherwise it won't work. And then the last bit is the output function. Here we have an initial mass function here. We have the mass distribution here. This is just the usual piece of Perl you'd use. So we have the hash for the initial mass function is this one. What we do here is we sort on what are called the keys. These are the strings that we use to label it. We have to sort it because normally when you make a histogram, you want to sort it from lowest to highest. And that's what this does. That's just the default. Of course, you can change the sort function to do whatever you like. Sort of backwards. You could even not have a sort function, just output random numbers. But most plotting tools like it to be ordered, so it makes it easier. And then I have a print statement here, which just outputs the IMF with the mass as the first term, and the second term is just whatever we added up in the code. Very similar for the output mass distribution. Again, we sort through them, and we just output the list. Nothing too hard there. And what do we get when we run it? So when you run the script, you get a load of stuff at the beginning, which is the setup. So it has to compile in the bit of logging code you put in. There's a load of sort of debugging stuff that goes in there. Most of that you can ignore unless there's a problem. The next bit is where it says run FlexiGrid. The FlexiGrid is the automatically generated grid that it runs. I can't remember why it's called that. It's old. And you get a list of lines every 30 seconds or so, or maybe, which will tell you we're running star 10, then star 20, then star 30, and so on. Go all the way through until you get to the end here. Okay, and you see here it's got, in these lines, these will be colored on the screen, so it'll be not easier to see. But, they're telling you binary is 0, gives you the mass as you go through, and it starts at 0.1 and ends at 80. But remember, it's centered grid cells, so it's not quite 0.1, it's not quite 80, because it's slightly offset. But it gives you a percentage completion here, and this is an estimated time to finishing. Notice that this says 19 minutes. Actually, it took about 30 seconds, maybe less. The reason, I'm sorry, 50 seconds. The reason it's got a bad estimate here is because at the beginning it's got a lot of setup stuff. So give it a few seconds to settle into give you an estimate. It is just an estimate. It may be wrong. And that estimate relies on each star taking the same time, which of course is not real. Massive stars, they live much less time. So. And if you have binaries, of course, it's a complete mess, because if you have one binary that has a lot of mass transfer, that may be very slow. So, but it does its best to estimate. It tells you that TPR is the time per run. Okay, that's each star takes roughly that much time. ETF is the time at which it estimates, its estimated time of finishing, I think it is, in this case. The PID is the process ID. That's so if you want to kill it, you can. It's very easy. And the memory here, this is the memory allocation of the grid and all of the sub-processes, looks like. Okay. So this will tell you how much RAM your grid is using. And if you see that going up into the multi-gigabytes, then you need to rethink what you're doing. Usually they'll fill the machine.
Is that in megabytes?
Yes. Yeah. And it tells you how many stars you run and what the total probability of the grid is. That should be nearly 1. If it's not, then you're in trouble. But you may be running a part of the grid. So if you're only running stars between 1 and 6 solar masses, then you don't expect that to be 1, because you're not covering all stars. But if you're running from 0.1 to 80, that's pretty much all stars in existence. So you should get 1. Then it will tell you that the grid is finished and it's joining the threads. And where it says be patient, it means it will take a few more seconds. It's just waiting for it to flush the data from the few remaining processes. Because what happens is that when you run the grid itself, it farms off to separate threads, all of these different processes in little queues. It just has to wait for those queues to finish and send their data back. That just should take a few seconds. It shouldn't take too long. Next is the number of failures. Now, I should change probability to actually read probability, but number of failures is 0. That's a good sign. Okay, that means none of the stars have failed. Now, remember we had a long discussion yesterday about why I overwrite the exit code or the exit command in C and I don't let you use it. That's because when it fails through the exit binary C, it then detects them in binary grid. If you just used exit directly, it would just stop. And that's not good. So you don't get any idea of what's failed. Now, normally you want failures to be 0 or at least a small number. Binary C shouldn't fail. When you're developing new code, it will. You'll always get something wrong. That's fine. But normally it should be 0. Then it tells you how long it took, and no systems failed, which is good. So it's okay. And then you get a series of output. Remember, we put those loops to output the IMF and the mass. Well, that's what we get next. So the IMF is this. This is the mass, so 0 is actually between 0 and 1, 1 is between 1 and 2, and so on. And you can plot this in your favorite plotting tool of choice, whatever that may be, and you find that it looks like Cooper IMF. The mass function itself is this one, which loops all the way up to 80 as well. And these have different numbers, of course, because here you're multiplying by the time step. So you're going to have to normalize those to find the mass distribution. But you can just plot it and it'll give you an idea of the shape. Yeah. That's fine. So you send them to your plotting. I should emphasize what I do not want to do, despite some people asking me to do this in the past, is to write plotting tools for you. I do not want to write statistical analysis tools for you, because you've all got your favorite way of doing that. I like to use GNU plot because I'm kind of old-fashioned, because I know how it works, and it's very easy to get great plots from it. You probably want to use some Python thing, or some people want to use R or something like that. There's always different kind of statistical tools. I'm not going to be here to tell you which ones you should use. Everyone has their favorite. It's up to you. Go and look on the web if you want. That's really something that other people can do. But what you can do here is just output the data, and then you can do whatever you like with the data. That's what it's for. Now, a quick thing before we finish on using slurm and condor. Here I've put a slurm example. You can set a load of variables in binary grid to control slurm. So slurm is a multi-machine queuing system. Condor is very similar. We have both here, actually, so it depends which system you use. Binary grid has a lot of software in it set up to automatically do this for you. You don't even have to write the scripts. It just does it for you. So this is what I would usually use for that. Now, you can change things like number of jobs you want to use. So how many machines you want to, or how many nodes you want to use. You have to set slurm to 1 here if you want to use it. I should say, if slurm is 0, it won't work. That's fine. You should have a working directory, which here I've set up, which is my slurm control directory. That's because you need to put the standard out, the standard error, and things like that, and log files, you need to put them somewhere, and that's where they go. You can tell Slurm how much memory to use per job, how much to warn. These are Slurm options. Normally you want end tasks to be 1 because you want each node, well, each node is usually 1 CPU, but it depends. You've got to know how your Slurm cluster is set up to know that, whether you should set that to the number of CPUs or you should just set it to 1. 1 is normally correct. And then it will fire as many jobs of that as it needs to. So they run as single thread jobs, but that's absolutely fine. Postpone join, what that means is, so okay, there are 2 ways to run something on a cluster. You can either run all of your jobs and then have them save their data, which you then have to join manually. You can do that by calling the script with join command equals join or something. It's very easy to do. And you can see it in the manual detail. That's fine. The reason that you might want to do that instead of have it automatically do it, because if you set that to 1, what it will do is the last one to finish will automatically join it and just then call your output function. The problem with that is then the joining is done on the node rather than on a machine of your choice. And often the joining may require more RAM than your node has, because you are joining from, let's say you've got 50 nodes here, that's 50 lots of data. Each node on its own is only doing 1/50th of the total data, but you may need more RAM. So you can then postpone the join and do that on a machine that maybe has more RAM or maybe is closer to your NFS, your networked file system. So it might be faster. I mean, if you can run it on the local machine where the data is, even better. So that's often what you want to do. Then you've got things like the slurm partition. That depends on how it's installed, I should say. I mean, this is what we must use for ours. I don't know, I can't remember much about slurm, so you can work that out for yourself. The job name is very useful. This is what slurm lists as your job name when you run the slurm view command. Use all node CPUs, that's related to the end tasks thing above. And then a slurm time is the time limit on your job. Okay, now I don't know how long it's going to take to run your stars. That depends how many you throw at it. We have to set a time limit on our jobs, otherwise it won't accept them. Okay, so normally you want that time limit to be much longer than you think your grid will take. It will take you a little bit of trial and error, I think, to work out what that is. You can say, oh, 1 star takes this, and so how long will the grid take? That's fine. But again, it's not obvious upfront how long each star will take on your grid. And of course, what happens if there's an issue on one of the nodes? Then you might have a problem. So you might have to rerun that. But it's pretty straightforward to set up the slurm stuff. So you can just then run it, you can throw it at the grid comes back, and your data is just sitting there, just like you run it on your multi-core CPUs. So you get, the whole point of this is that there's not extra work for you other than this little chunk. Now, I was going to show you the yield versus time. I don't know how to.
So will that script only create the slurm job file?
No, you run it.
Okay.
It will launch it for you. Slurm job files are not quite the same as Condor. So the way it does it, it uses Slurm arrays to run multiple jobs. Condor is a bit different because Condor, you have to have a different startup script, or at least an old Condor, I don't know the new one, but you have a startup script for each of the jobs. So in Slurm, you have 1 job with 50 array parts on it. In Condor, you have 50 jobs. It does the same. It's just a slightly different way of managing it. Now, I was going to show you yields versus time. This is very quick. I've got to find out, can I share a screen? Does anyone know? Or do I have to share an application? Desktop. I can share a desktop. That's what I want to do. Where? Desktop 1, desktop 2. Okay. Now the question is, which of my desktops is this? They all have windows in. I guess this one. Anyone know how I actually get the desktop to show anything? I got 6 desktops, and this is not any of them. Pretty cool. That's very odd, isn't it? All right, let me try desktop 1. That works for sure. Super. What's this thing here? Anyone know? Go away. Hey. Super. Okay. What I quite like about Zoom, it doesn't allow me to have an infinite Pink Floyd type effect here. It should be zooming in continuously. It's pretty smart in that regard. What I'm going to show you is the yield versus time script. I need to build that. Okay. So in here, and this is my lovely Emacs colors, for those of you who don't know my Emacs colors, they're very low contrast, so they're very good for your eyes. In binary C parameters, there's a step you can put in called, oh, where is it? Oh, sorry, it's in nukes-in parameters that we have to build for this. There's this one called the nukes-in GCE. So we have to build that, and what that does, it sets everything for galactic chemical evolution. So what I'm going to show you is the stellar population ensemble that I use, and also the stellar yields. Now, these are two things that are built in, and I think we can use these to construct sets of data, which you can then put into, say, cosmological simulations, which will give you the number of stars as a function of time of many different types. It will give you the rate of supernovae as a function of time, the chemical yields as a function of time, all the data that you need. And probably this is much of the data that most people are looking for. The way to run this, then, is, so if we go to, let's go back in here, into the build directory, I can try building this. I haven't broken it. There we go. So this is Ninja building it for us. It's pretty fast. You can see on the left there, the file number is going up as a function of time. Make it a bit bigger. So see what is it? There we go. But it works. It mostly works. There's still a couple of little bugs in the center. While that's working, I go to my Perl directory. I'll install that. It's not as fast as it would be because Zoom's taking all the bloody time. Now, I've also set up autocomplete on Ninja. If you want to know how to do that, that's also written in the binary C manual. So, for example, if I press space, these are all my Ninja targets. So it's very easy to set up. But the one I want is the classic binary C install legacy. And that's now installed binary C, and it tells you all of these things, which are the API functions which are available that it's installed. Now, I told you before that when you rebuild this, you have to also reinstall the binary grid module. So let's do that. You get all the stuff about how it's compiling, blah, 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 and it's done. So here you've got OK, which means that it should have installed OK.
I have a question. Could Ninja do this as well?
Sure. In theory, it could, but it would rely on knowing about your Perl installation, which may or may not be your local installation. It's a bit complicated.
So not like a current Perl environment variable.
There's a Perl brew environment variable. But again, there are standard ways to do this, and there are non-standard ways. Some people use non-standard ways. So, I actually have this script set up so I can call the watch command, and it just sits there and it installs when I reinstall the library. It installs automatically. So, other people, if you want a copy of this, I can send it to you. It's not a problem. It's very simple. So everything should now work. Template, yields versus time. Now, if I call yields versus time, it will complain to me while it loads everything, which is great. So it's this is a good sign. It's got all this stuff here, which is from binary C config. That's nice. It's got all the stuff here, so it's defining all the functions we need. It says there's no time step given, which is good. What I want the time step. So I need to set a time step. There are two ways to run this script. One is with log times, one is with linear times. but I'm going to use log times because it's easier. I'm going to set a start time to be 1 megayear. The reason you have to do that when you have log times is because otherwise you can get back to minus infinity. That's not good because 0 is minus infinity. Let's choose a metallicity to be 0.02. That should work. What else do I have to set? Probably that's it, I think. It automatically chooses the output directory to be based on today's date. That's what this line does here. That's easy. If I go through, these are very similar to what we had in the previous one, but it's a bit more complicated. But you see all the different physics is set up here. These are all the options you can pass in. Choose what you want. These are all the options we talked about yesterday, which is good. Yeah, here's where we set up the grid. Now I've set the stars to be single stars. I'm only going to run single stars because binaries take a long time. And we're trying to demo it. That should work. There we go. And now it's running 235 stars for us. Give it a few seconds. Zoom's taking most of my CPUs, so it's struggling with Zoom, but that's okay. And we'll leave that to go. So while we're waiting for this to finish, do we have any immediate questions on how these things work? Oh, it's finished. There we go. So this is the bit where you have to wait. And you see it's waiting for these jobs. It's got numbers pending. That's because the queues are not quite finished. Each CPU has a queue. It's just running through the end of the queue. Give it a few seconds. It'll be done. And now it's done. So now if I look in my data directory, data pops, notice I have a directory from today, 3rd of December. Let's go in there, and I have a load of data sitting there. This is what's output by this. There are 2 sets of files, the ensemble and the yields. There are 2 sets of yields, actually. These are symbolic links to these. That's because there are different sources. So you've got the AGV source, the Wolf-Rayet stars, the supernovae. These are all numbered, but there's also a symlink using a name that you can actually read. It's quite useful. Now, what I'm going to do first is run the plot ensemble script. So, well, I can show you what's in the ensemble file. It tells you what all the columns are. It's very easy. Essentially, the first column is the time, and then you have the number of stars of each type. There are lots of different types. So that's because real life is complicated. They've also got rates of mergers and things like that. Lots of different supernovae. It also gives you all the modules that are installed in Perl, and it gives you all the options that are set. The reason for this is so that you can go back and you can look later and debug if you need to. And this is what the data looks like. So it's the first one is the time. So here it's log t is 0.7, and then you have all the different types of stars are listed as just numbers. It's statistics. It looks awful to us, but computers don't care. It's fine. But I have a plotting script which will plot this for us. Take a few seconds. I can also do the same for the yields. That will take a little bit longer. Especially because the plotting takes a few seconds. Someone tell a joke. Dutch jokes? Come on, Dutch side of the table, yeah. Some Dutch jokes.
That's racism again.
How's that racism? Just leave that in the background.
There are as many Dutch people.
There you go. See, that's racism.
Oh,
So from the ensemble output, you can get. I've got 107 different plots in here, but in binaries there would be more because I've only run single stars, so there's no double degenerates in this. But you can look at things like number of black holes as a function of time. That gives you that immediately.
So it's possible for anyone to, within their custom thing that they want to go
Yes,
and watch,
of course,
right? Yeah.
Of course. I've done that. I have done that for many people. So
Exactly.
there's a function called the Euclidean ensemble where it defines what each stellar type is. So it defines what a black hole is. Right? It's easy because it's just when the stellar type is black holes. But it can be more complicated than that. So yeah, I'll show you some of those in a second. You can also show the black hole luminosity is tiny, so it's kind of pointless. But This is a good one. This is the number of blue supergiants as a function of time, for example. You can also do blue supergiant luminosity as a function of time. Okay. Number of core helium-burning stars as a function of time, or the luminosity in them. I mean, it's the same thing, just multiplied by the luminosity. Very easy. And you can go through and you can look at, say, number of carbon motes from white dwarfs and so on. And we have 100 odd different plots. You see the resolution's not quite right because you've only got 125 stars. You can run it with many, many more. You'll see in that script that the time resolution is chosen such that, well, the masses of the stars are chosen so that you put exactly the right stars in each time bin. Okay, because you know how long a star takes to live, right? Because you know roughly its main sequence lifetime. And actually it constructs a table for you to do this. So when you want something like this, you want to put, say, 4 stars or 5 stars in each time bin. You don't want to put 100 stars in one time bin and 1 star in another and 0 in another. And a traditional grid will do that. This is a smart grid. It will actually go through and pick the time resolution to fill these plots as well as can be done. And you can then say, what is my sampling in this? You can say, I can have 4 stars in there or 10 stars in there. Or 100,
But you mean it's a variable bin width?
no, the bin width is fixed because that's 0.1 and that's in log time. So you have to vary the mass of each star that you choose in the grid to put them in the right bins. And it does that by setting up a lookup table at the beginning. It does it numerically. It doesn't do it assuming main sequence time or anything. So you can use any code.
But it does that after it's run the grid.
Before it runs the grid. So it runs a sample of stars before, and then it runs the grid after them. But it caches that sample, so you don't have to do it twice, which is useful. But I can go through this later if you want. But it's the smartest way you want to do it. And then you can go through and you can look at all these different types. Let's see if we can find we've got things like this, like sort of mass in stars. You can see how that drops with time. Right? For example, that's just stars blowing up at the beginning. And you see, actually, it doesn't make much difference to the whole population of blow up stars. We sort of blow them up here. Stellar wind is continuous, and that keeps moving down. This is just the number of stars. And of course, the number is not the same as the mass, so you can count them differently. And luminosity in main sequence, stuff like that. So young populations are brighter. That's not surprising. Number of neutron stars. Well, they peak later than the black holes, a little bit. And by the time you get to here, you're done. That's your 8 solar mass, and so on. And you can do neutron star luminosity if you care. So you've got all these different variables, and you can go through and you can decide which of them you really care about. That's up to you. And maybe you need to increase the resolution to get the right ones and so on. There's things like this one. This shows you that you've got to be careful. These are massive O stars. These are white dwarfs that sit on in the O star because they get very hot very quickly. It's not the same as the luminosity. Just because you have a lot of them doesn't mean that they're very bright. So these you probably would never see. These you certainly would. So you've got to be careful. And you can see that from the luminosity. This is the luminosity of the O-type stars at early times. This is later, and this is clearly many orders of magnitude. Okay, so fine. And if you're worried about these spikes, remember this is a very low resolution run. So you can run it higher. You can also increase the time resolution. You can do whatever you like. And the other thing I wanted to show, just to finish off, was the yield sets. These are the chemical yields. So it's kind of the same thing, but for different elements. So here I've got the rate of ejection of mass as carbon-12 divided by the mass into stars. And the reason you want to do that is because when you're running a chemical evolution code, at each time step, you've got a mass you form into stars. That's what we multiply by this. And then you convolve these functions to get your yields as a function of time for a real population. I have scripts that will do that for you as well. It's very easy to do. And here you can see which source makes the different type of, or in this case, carbon. So it's mostly because this is high metallicity. There's a lot of Wolf-Rayet stars that output because massive stars have a lot of winds. You get the source here, which is from AGB stars coming later, so they dominate in later times. Here you can say even at very late times, it's the red giant branch that dominates. That's because one solar mass star probably loses most of its mass on the giant branch rather than the AGB, and it doesn't have very much carbon. Right? So it looks pretty good. things like carbon-13. We have a lot of isotopes, which is why the plot took ages. We've got 385. There's actually 400 and something. You can go through and you can decide which ones you care about. I don't know. We have iron 56. Let's try that. There you go. People care about iron. People always like iron. And most of it comes from supernovae. That's a surprise. This is only single stars, of course. You want binaries, takes longer, and you'll have a low binary signal. But all this stuff is there and free for you to use. So, and it probably does everything you want already. So I think that's where I should end, because I want to let other people talk. Do we have any questions? Any questions from anyone? Anyone online? Still alive?
Can you guys hear me?
Yeah.
Just one question. So in all these plots, there's no star formation rate in there yet, right? That's purely just a burst at time 0?
That's exactly right. And then you can, there are scripts that I have which will put in a star formation rate and integrate through these for you. So you can do it. It's
Cool.
just
checking.
so, but it's the raw data that you would want to put into, say, chemical evolution codes, or indeed into cosmological codes or things like that. So.
Okay.
Any other questions? No one at the back? Very quiet. Morgan's looking confused.
I'm always confused.
That's all right.
I guess you can't easily do synthetic photometry.
In what sense?
Well, suppose I wanted to take this and go, right, here's a cluster, what are its BRI magnitudes?
Oh, of course you can.
You need model spectra, right?
No. There is a module in the code which uses, I think, colors from Kuritz from some while back.
Oh, but then
So you can do those.
That is model. You attach a model.
Somebody else has done that modeling, but you're mapping from log G and temperature or luminosity or whatever to the colors.
Okay.
The Kuritz ones are okay. There are also Gaia colors in there, and there are Johnson colors and the other ones. Yeah, there's HSD filters as well. I would like somebody who knows what they're doing to test this code, because I don't. I'm not an expert in this. At which point I will trust it more. And that's actually one of the things I was hoping, having you lot here today, was can we find a way to test these to make sure they work? Because I put the code in and I took it from various places, but I'm not an expert. But we do have that data. It's there. Yeah. So you can do that. Absolutely.
And the other question I had is for the chemical yields, how is our process stuff? Would you trust it?
So the R process that's in here at the moment is taken from, say, Simmerer's paper, which is essentially you take the solar abundance, you subtract what you think the S process should be, and that's your R process.
Okay.
Would you trust that? No, because that's clearly phenomenological. It's not really a model as such. I'm very happy to input some, say, neutron star R process yields. If you can tell me where they are and get me a table of them, I can put it in. That's harder to do, because most people that publish these things, they don't publish tables. They just give you plots. And assuming they even give you plots, which they probably won't. So it's pretty hard to do. But if we can persuade the authors to do it, anyone has access to Star Trek, you can probably steal it from them. Because they had a paper out recently. I'm not sure we should steal things from Star Trek. Just for the record, they're nice people. I'm sure they give us the data. But if you can give me a table, I can put it in, because we got the number of neutron star mergers as a function of time, so you could easily do that. I mean, that's what we do for 1A. People who do 1As are much more likely to publish their numbers, which is, I don't know why. Maybe it's because they're a more established field. I don't know. I'm not sure. Maybe Evo's a nicer guy. Maybe someone knows a source of neutron star yields that we could use.
Hypernova.
Neutron star mergers.
Yes, hypernova.
Or neutron star black hole mergers. We need those.
Well, yeah. A while ago I looked into this, but there's not that much information about this yet, or it's a very new thing, right? But I did find some PhD thesis of someone that worked out that whole network.
So there are people who've done it,
Yeah.
but it's just getting the data is not so easy.
Well, sending an email might be the first step.
Absolutely. If someone's willing to do it, please do. I haven't got time, so I'd like someone else to do it. I'm very happy to support the code.